All right, I'm going to start a new module that is entirely different from any of the others because this module doesn't really deal with um, the fundamentals of structures. It doesn't deal with reactions. It really deals with the question of how do I know what's in a flask in a lab? We get chemicals, we pull them off the shelves, and we assume that they have in them what we think they are, what they're labeled as. And when we run a reaction, we can assume that the product that we created is what we think it is. But assumptions don't really do justice to our work. We really want to know. That's what scientists do. Um, so the question is how do I know what's in a given container? What kind of molecules are there? Um, the thing is, molecules are too small. We're never going to be able to see them. Um, and so, over the course of the history of chemistry, chemists have had to come up with different ways to characterize substances so that they could say, I think I made this compound, and here's my evidence. Um, there were uh, some methods that we still use, um, you know, noting the phase at room temperature, whether it's solid, liquid, or gas, measuring the melting and boiling points. Those are definitely used to characterize substances. Looking at the color is definitely a good one. Some things have very distinctive odors. Um, One thing that we don't do in the lab anymore is taste chemicals. This is something chemists definitely did a lot of in the 19th century, maybe even early 20th century. The thing is, chemists also had a bad habit of dying young, so we don't really want to taste any chemicals now. Um, but chemists would characterize what they would react with. They would characterize various physical properties, and then try and say, okay, this is my evidence that this is the substance I have. Now, the thing is, with organic compounds, you have seen at this point that there are basically an infinite number of possible organic compounds that we could have. Um, and so, in many cases, characterizing them by all these physical properties is not necessarily going to get us a unique identification every time. Uh, so we have had to develop different ways of probing molecules. Um, and generally, that probing of molecules ends up using the light spectrum, the photoelectric, photomag- electromagnetic spectrum. Sorry for the brain fart. The electromagnetic spectrum, um, in many cases, is used to probe molecules. And so those techniques are called spectroscopy techniques. Um, and I want to explain how a few of them are used in organic chemistry. Um, the three that we'll look at would be mass spectrometry. This can really tell you the chemical formula. So it could tell you, okay, this compound is C6H uh, 14O. Um, so that's a start, right? Now, you've seen from early on in this course that just knowing a chemical formula narrows it down, but still, I could draw, in many cases, 1,000, 2,000, 10,000, 100,000 different isomers with the same chemical formula. Um, so mass spectrometry is a good start. It'll allow us to say what the chemical formula of a compound is, but we're going to need more. Um, we'll also look at infrared spectroscopy or IR spectroscopy, um, and that can tell you about some of the functional groups. That might be present in your molecule. Uh, so also a very useful technique, right? It might be able to tell me, uh, for instance, that I have a carbon double bonded to oxygen. All right, that's a useful piece of information, but still, just knowing a chemical formula and knowing uh, some of the functional groups doesn't give me one unique molecule either. So we need further techniques. The last one we'll talk about is called NMR spectroscopy, nuclear magnetic resonance. And this can tell us about the chemical environment around specific atoms. Specifically, uh, we'll focus on the hydrogen atoms. Uh, you can also do this with the carbon atoms, but the hydrogen atoms, because there are more of them generally, um, we're going to get more information from the hydrogen NMR spectra. So we'll talk about those three techniques and how you can put them together to take their, let's say, the product of a reaction, um, and really characterize it and say what that substance is. All right. I'm going to start with mass spectrometry. It's in some ways the simplest, um, and it's not one that I would ask you to actually learn all the ins and outs of. But I think it's helpful to have some background on how it works, because just to say, oh, it tells us the chemical formula without giving you any idea of how it does that, um, isn't necessarily the way I roll. I like to give you at least some basis for understanding it. Um, so the idea is this, okay? We send in molecules into our mass spectrometer. This is a very rough sketch of what a mass spectrometer would look like. And we are going to send in a stream of molecules. I'm going to call my molecules M. So M is my molecule. Um, when I send my stream of molecules into the spectrometer, it first will pass through an ionizer. Okay, what an ionizer does is it turns my molecule into ions. This will essentially knock an electron out of my molecules. All right. So as it goes through the ionizer, it turns into M plus. Now, the thing is, once you knock an electron out of a molecule, that molecule often becomes unstable, and some of the bonds will start to break. So M plus will start to fragment. Uh, and the thing about each of those fragments is they will have different masses. So I have my molecules. Some of the M plus stays together, some of it breaks up. Um, and as those molecules start to continue to move through this chamber, we actually have a magnetic field in the chamber that is pushing them toward a detector. Okay, so when they enter this chamber, there's a magnetic field pushing them downward. So all of my particles are going to start to follow a curved path, um, because this magnetic field is going to cause them to accelerate down towards the detector. Now, the the molecules of M plus that stay together will go the farthest because those are the heaviest ones. And if you think about it, um, think back to physics. Force equals mass times acceleration. The force on all these ions is going to be the same because these ions all have a +1 charge. Um, but the heavier they are, the greater their mass. Uh, Thinking back to physics, if F equals ma, then their acceleration is going to equal the force divided by the mass. Uh, since they all have the same force, the magnetic field applies the same force to all the particles because they all have a +1 charge. The heavier particles are the ones that are going to be harder to change direction. So they are going to go the farthest. Okay, so M plus is going to go the farthest on my detector. Some of those lighter fragments will break off earlier and hit the detector in different spots. So lighter particles don't travel as far because they get accelerated really quickly down toward the detector. Okay, and our detector is essentially going to produce a graph that shows the relative number of particles that travel a certain distance. And so this x-axis in the graph is mass divided by charge, but z, the charge, is +1 for all the ions. I mean, there may be some fragments that and a tiny fraction of fragments that end up with different charges, but um, +1 is essentially the same for all of them. So this x-axis is really representing the mass, and it's generally in atomic mass units. So you can think of this as being mass in atomic mass units. That's what this graph shows. And it will show how many particles of each mass uh, there are in my sample as the molecule fragments. Um, so why is this useful? Well, if we look all the way over on the right side, usually this big peak over here, this will represent M plus. And so this peak there will represents the molar mass of the compound. Now, you might be asking yourself, don't I see if I zoom in down here, don't I see two little peaks right over here? Like, what's the deal with those two little peaks? Um, so let's talk about those two little peaks. And in order to do so, we're going to have to talk about um, isotopes, which we haven't really talked about in this course. You hopefully talked about it in your first year of chemistry. Um, but we know that not all carbon atoms have exactly the same mass, and not all hydrogen atoms have exactly the same mass. So carbon is about 99% carbon 12. Um, Remember, carbon 12 has 6 protons and 6 neutrons. But then 1% of roughly 1% of carbon atoms are carbon 13. So they have 6 protons and 7 neutrons. All right. So if I think about a sample of ethane, um, about 99% of the time, I'm going to have 2 atoms of carbon 12. Um, with hydrogen, hydrogen is like 99.9% hydrogen 1, just 1 proton, and like 0.1, it might even be closer to 0.01% hydrogen 2, or what we call deuterium. Uh, so you are going to have some molecules that have a carbon-13 atom. You're going to have some molecules that have a hydrogen-2 atom, right? And if we think about their masses, the mass of most ethane molecules will be 12 plus 12 plus 6. Um, so 12 plus 12 plus 6 is 30 grams per mole, or 30 AMUs. But then you're going to have some that are 31 grams per mole. You might even get the rare occasional molecule that is 32 grams per mole, because there are two carbon-13s, or there's a carbon-13 and a hydrogen-2 in the same molecule. So if we focus on the very right-hand side, generally we're going to see a tall peak. This is focused on the right end of the spectrum. Generally, we're going to see a taller peak, and then next to it, so the taller peak will be M. The peak next to it would be M plus 1. Occasionally, we even see a really tiny M plus 2 peak. So that end where we see those tiny little peaks, the reason we're discounting those is those represent the rare isotopic outliers. And that's why we see that pattern at the far end, right end. So we can be pretty sure that this right-hand peak that's relatively tall is going to represent the molar mass of the compound. All right. So that's gonna be really helpful. There are some uh, elements that have very distinctive isotopic ratios. So for carbon, it's like 99 to 1. For hydrogen, it's like 9,999 to 1. But for chlorine, its two most common isotopes are roughly a 3 to 1 ratio, 75% and 25%. Because of that, we would expect to see at the right-hand end of a spectrum of a molecule of a molecule containing chlorine, we would expect to see an M peak and an M plus 2 peak, where those are present in roughly a 1 to 3 ratio, right? So if we call this a height of 1, let's see if I can carry this out. I'm going to try and show that this, if I duplicate it 3 times, 1, 2, 3. All right, didn't work out exactly as I wanted, but notice there's roughly a 1 to 3 ratio in height between those, because roughly 75% of my molecules have chlorine 35. Roughly a quarter of them have chlorine 37. So when you see a spectrum like this, where you have a 3 to 1 ratio between an M peak and an M plus 2 peak, that's a hint that there's chlorine in the molecule. All right. And, using all those isotopic ratios, we've figured out how to read these spectra and get a very good idea of what the molar mass of the compound is. You might say, okay, molar mass, that there are different ways to come up with the same molar mass. So, for example, you might have a formula of C4H10. Okay, that's got a molar mass of 4 times 12 plus 10 is roughly 58 grams per mole, or 58 AMU. I could also have C3H6O. That's got a molar mass of 3 times 12, which is 36, plus 6 plus 16, which is also roughly 58 AMU. This is where a lesson that some of you haven't encountered before. If you've taken AP Chem, you have. And that's the idea that we can measure things to a different level of precision. Um, and it matters how precise our measurements are. Um, so if you've never heard of significant figures before, I'd be happy to talk about them with you. If you have heard of significant figures, this is a case where significant figures really matter. Because if I can measure two more decimal places, I can tell the difference between these two. Because in actuality, carbon C4H10 would be 58.0783 AMU, whereas C3H60 would be 58.0419 AMU. All right, so if I have a high resolution machine that can really differentiate what the molar mass of the particles is, I can actually make this distinction. So the bottom line, what I'd like you to take away is that mass spectrometry is a technique um, operating on a relatively simple principle, the idea that if we ionize a molecule and then pass it through a magnetic field, we can compare the masses of the different particles. Um, we can get a sense of what the molar mass of the heaviest particle, which represents the molecule itself, is. Um, for our purposes in this class, we're ignoring the mass of all the fragments, although there is a whole body of research around how molecules fragment, and so the different fragments can give an experienced uh, chemist more information. But the bottom line is, in the end, what we can do is come up with what is the chemical formula for our compound by using this technique. And so that's something that chemists often turn to, um, running their samples through a mass spec to figure out the chemical formula. Okay, um, so I'm going to close this part there, and then the next thing that I'll talk about will be infrared spectroscopy, which is where we get information about how those atoms are bonded together.